Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now let's get started on our set of questions for today's session. Okay, so question 1 says to write Lewis structures for CO3 2-, HCO3-, and H2CO3. When acid is added to an aqueous solution containing carbonate or bicarbonate ions, carbon dioxide gas is formed. We generally say that carbonic acid, H2CO3, is unstable. Use bond energies to estimate delta E for the reaction in the gas phase. Specify a plausible cause for the instability of carbonic acid. Okay, so the first part of the question asks to write all the different Lewis structures for all these different ions. So let's start with carbonate ion, CO3 2-. So to find the Lewis structure of anything, we need to find first the total valence electrons of the compound. So for carbon, it has 4 valence electrons. For oxygen, there are 6 valence electrons. And since there are 3 oxygen atoms, I'm going to multiply this by 3, which gives us 18. And then finally, there's a -2 charge on the compound. So we are going to add an additional 2 electrons. So in total, this gives us 24 valence electrons. So now I'm going to start off by writing my carbon in the middle. Let's do a different color. Let's write my carbon in the middle. And then I'm going to draw my 3 oxygens, all single bonded. Okay, so let's recall that for every single bond, there are 2 electrons participating. So far I've drawn 6 out of the 24 electrons that I should have. So now I'm going to then draw all of the lone pairs on oxygen. So each of them contain 3 valence electrons. And now let's count it out. These will all have negative charges as well. If we counted out how many I have drawn now, each oxygen has 1, 2, 3, 4, 5, 6 valence electrons. There are 2 electrons in every bond, so that's 8 times 3. So I've drawn 24. But if you look at our central carbon atom, you'll notice it doesn't have a full octet. So what we need to do now is form a double bond. And to do that, I can show one of the oxygen's negative charge come down to form a double bond so that our carbon has a full octet. So now we can draw out pretty much the same thing. Except now there is a double bonded carbon, oxygen bond, and only 4 valence electrons on that oxygen. Okay, so now let's double check that we have our 24 electrons, 1, 2, 3, 4, 5, 6, 7, 8, plus 8, 16, plus another 8, 24. Okay, so the correct Lewis structure I will box in green for the carbonate ion. So now let's do the same thing for one of the bicarbonate ions, HCO3 minus. Let's find its total valence electrons. Carbon is 4. Oxygen, 6 times 3, which is 18. And then this ion only has one -1 charge, so I'm going to add 1 electron. And what I also need to write is that there is a hydrogen which has 1 valence electron as well. So this will also give us a total of 24 valence electrons. So this is pretty similar to our first ion, which makes sense because it just has a proton added. So I know I'm going to need a double bonded oxygen. This carbon will be bonded to 2 oxygens, except this time one of the oxygens will contain a hydrogen. So this is now the structure for HCO3 minus. And let's double check the number of electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, plus 16, 17, 18, 19, 20, 21, 22, 3, 24. Okay, so this is the Lewis structure of HCO3 minus. Okay, so now let's do carbonic acid. Carbon, 4 electrons. Oxygen, 6 times 3. Hydrogen, there are 2 this time, so it's 1 electron times 2. So the total valence electrons is 24 again. Okay, so I'll draw here. There will be a double bonded oxygen to the carbon, and it is bonded, single bonded to 2 oxygens. And then each of those oxygens has a hydrogen attached. Okay, so now I'll just draw all of the lone pairs that are missing. And this is our final Lewis structure. So we can double check and count out all the electrons. 4, 5, 6, 7, 8, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so this is the final Lewis structure for carbonic acid. Okay, so now that we have all the Lewis structures written down, we can get to the second part of the question. I'll just label it as 1B. So I'm going to first draw out the chemical reaction. So this was already given in the question. And it might be easier to just show this reaction and also showing all the bonds and the reactants and the products. So we know from the previous step what the Lewis structure of carbonic acid is. And the structure for carbon dioxide is just carbon double bonded with 2 oxygens. And the Lewis structure of water is just oxygen with 2 lone pairs. Okay, so this is just pretty much showing the reaction with all of the different structures. So when we want to use bond energies to estimate delta E for the reaction in the gas phase, it's easier to just make a table showing all the different bonds that are broken and formed. So we have 3 types of bonds for all 3 of these different molecules. So we have a single bonded carbon and oxygen as one of the bonds. There's also a double bonded carbon and oxygen bond. So this is in carbonic acid and also in carbon dioxide. And there is also a single bonded oxygen to hydrogen bond as well. Okay, so that's one of the columns. The second column will be the energy of all of these types of bonds. So this might be given in the question, but I'm going to Google just a bond energy table. Yes. Okay, so let's just try to find one of them. Let's use this one. It's kind of clean. Okay, so using this table, a carbon-oxygen bond has an energy of 358 kilojoules per mole. A double bonded carbon-oxygen bond, 805 kilojoules per mole. And then a single bonded oxygen-hydrogen is 464 kilojoules per mole. Okay, so that is our second column in this table. And what I also want to write down are the number of reactant bonds for each of these bonds in the table. So we just need to count out how many single bonded carbon-oxygen bonds there are in our reactant. So if we count it out, we'll see that there are 2. How many double bonded carbon-oxygen bonds in the reactants? So there's only 1 in carbonic acid. And lastly, how many oxygen-hydrogen bonds there are? There are 2 as well. And then let's do the same thing for our number of product bonds. So now let's look at carbon dioxide and water. So how many single bonded carbon-oxygen bonds? There are none. How many double bonded carbon-oxygens? There are 2 in carbon dioxide. Lastly, how many single bonded oxygen-hydrogen bonds? There are also 2, and they are in water. So now we need to find delta E for the reaction. So that just means like delta energy, but I can also denote it as delta H. See what they use. Yeah, I'll just use delta H. So delta H is equal to the sum of your delta H of formation of all of the broken bonds so all the bonds that need to be broken are from our reactants, so from the carbonic acid. And this will be minus the sum of the delta H of formation of all of the formed bonds. So all of the bonds needed to be formed in the products. Okay, so now I can sub in all of the energy values and then show how many of those bonds are broken and how many are formed. So that's why it was helpful to write out the table. So let's look at all of the broken bonds. There are 2 single bonded oxygen bonds that were broken in our reactants. Those going to be 2 times 358 kilojoules per mole, but I won't write the units in for now. And then another bond that was broken was the carbonyl bond. So there's only one carbonyl bond, so we're going to add 805. And then there are 2 alcohol bonds that were broken. So it's 2 times 464. So those are all the broken bonds. And now I'm going to minus the sum of all of the bonds that were formed. So it is just the 2 carbon double bonded with oxygen bonds. So 2 times 805 plus the 2 OH bonds that were formed. 2 times 464. And those are all of our formed bonds. So if we add it all up, you get 2,449 minus 2,538, which is equal to negative 89. Yeah, negative 89 kilojoules per mole. So the last part of the question just asks, specify a plausible cause for the instability of carbonic acid. So the instability of a reactant depends on how stable the products it forms are. So if we look at both carbon dioxide and water, these are both stable. So this might help us kind of justify the fact that carbonic acid is unstable, because once it forms carbon dioxide and water, since these 2 products are stable, it's not likely they're going to react again to form carbonic acid. This might be a reason why carbonic acid is unstable. Okay, so now let's see what the junior tutor said. Going back to my previous page, they have the different probable Lewis structures of the carbonate ion. Okay, so they have all of the different resonance structures. So all of these are correct. So mine is the most similar to the first one that they drew. They have the bicarbonate ion. Yep, so any of these is correct. They have both the resonance structures. And then lastly, they have the Lewis structure for carbonic acid, which is the same as mine, so that is correct as well. Part B, they wrote out the helpful table to help solve delta E 358, 803, 464. So it depends on what book you use as a reference. So the table that they had has 803 instead of 805, but it's pretty similar. So depending on what you use as a reference, you might get slightly different values. They counted out the number of reactant bonds and the number of product bonds. And then they did the delta H, which is the sum of the delta H of formation of the energies of broken bonds, and then the sum of the delta H of formation of all the bonds formed. And they got negative 87 kilojoules per mole. So when H2CO3 decomposes, it forms two very stable compounds, carbon dioxide and water. That's why it's unstable. Yeah, so that's kind of what I said too. So this solution is correct. Okay, so now let's move on to question number 2. Question 2, what is the Lewis structure of Ni3? So nitrogen triiodide. Okay, so to write the Lewis structure, I first want to find the total valence electrons of the compound. So for nitrogen, nitrogen has 5 valence electrons. And for iodine, each iodine atom has 7 valence electrons, but since there are 3 of them, I'm going to multiply by 3. So I get 21. And then adding these two values up, you get a total number of 26 valence electrons in the compound. Okay, so now let's draw our nitrogen in the middle and a single bond to each of the iodines. And then now I'm going to draw all of the lone pairs on iodine. 1, 2, 3, 4, 5, 6. Okay, so after I write all the lone pairs on all of the terminal atoms, I like to count how many I have so far at this step. So each bond contains 2 electrons. So we have 3 bonds, so that is 6. And then I'm going to count out all of the lone pairs. So each of the iodines has 6 lone pairs. So 8 times 3, I have 24 drawn so far. And the remaining 2, I can draw as a lone pair on our nitrogen. Okay, so that gives us 26 valence electrons. Nitrogen has a full octet, so I can say that this is the Lewis structure for Ni3. Okay, so let's see what the junior tutor said. Lewis dot structure is a representation of an atom, ion, or compound that shows how the valence electrons of the atoms are distributed as bonds, lone pairs, and sometimes radicals. Drawing the Lewis structure of a compound may sometimes need some trial and error. However, we can follow some guides and rules in drawing it. Okay, so they have a step-by-step guide. Determine the central atom. So in our case, it was the nitrogen. 2, logically arrange the atoms. So this is when I placed all the 3 iodines. Thinking beforehand how many bonds an atom can create can be helpful. For atoms that follow the octet rule, the number of bonds an atom typically makes can be solved by subtracting 8 by the number of valence electrons of an atom. Yep, so that's one way to do it as well. Then you connect the atoms, adjust the number of bonds if necessary. 4, check if the rules below are followed. If not, make the necessary adjustments. 5, redraw the entire molecule if needed. So the rules. Make sure atoms that follow the octet rules strictly have 8 valence electrons. These are typically period 2 nonmetals. 2, minimize the formal charges of the atoms if possible. 3, more electronegative atoms are given the more negative formal charge if applicable. 4, make sure the sum of the formal charges matches the charge of the compound. Okay, so using these guides, they drew Ni3. The most logical central atom is nitrogen, since if it were a side group, it would be difficult to satisfy the octet rule for nitrogen. Step 2, the arrangement would be to simply place the 3 iodine atoms around nitrogen. 3, when a halogen such as iodine is not the central atom, typically follows the octet rule. Thus, to achieve the octet state, iodine, which has 7 valence electrons, would usually create 1 bond only. On the other hand, nitrogen, which has 5 valence electrons, would need to create 3 bonds to achieve the octet state with a 0 formal charge. Based on these, the total number of bonds the 3 iodine atoms need matches the number of bonds the nitrogen atom needs. To complete the Lewis structure, we just have to add the appropriate number of lone pairs to ultimately place 8 valence electrons to each atom. Okay, so they got the same Lewis structure I had as well. For the last step, let us verify whether the rules were followed. Okay, so they made sure of that. And they also showed the formula for formal charge. So all of the atoms had a formal charge of 0, so that was good. If we solve for the formal charge of each atom, we would see that they all have a 0 formal charge. Rule 3, more electronegative atoms are given the more negative formal charge, so that is not applicable in our case. And the net charge of our compound is 0, which matches the sum of the formal charge of the atoms. Yep, so the solution is correct. Spell. Okay, so question 3. Rank the following compounds in order of decreasing vapor pressure. Okay, so you have propanol, methanol, methane, and ethanol. Okay, so first let's define vapor pressure. Vapor pressure is the pressure exerted by a vapor with its condensed phases, either as a solid or liquid, at a given temperature in a closed system. Okay, so I'll just make some notes about the different functional groups of the compounds. So in general, alkanes, which are single bonded carbon bonds. So in this case, we have single bonded carbon hydrogen bonds. Alkanes tend to have a weak intermolecular forces. They have high vapor pressures. And they're also volatile. Alcohols, on the other hand, are less volatile. Okay, so pretty much we can say that the compound that doesn't contain an alcohol group, like the methane, will have the highest vapor pressure. So another note that I'd like to add is as the hydrocarbon chain increases, and the alcohol the boiling point increases as well. Making a less volatile alcohol. So this is due to dispersion forces. Okay, so knowing this, we can write our methane having the highest vapor pressure. And then the next one is our shortest alcohol group. And then I'll just draw the alcohols getting bigger and bigger. With our propanol having the lowest vapor pressure. Okay, so again, since our propanol has a longer hydrocarbon chain, since this increases the boiling point, that means we have less of it as a vapor form, making it the lowest vapor pressure for this molecule. Okay, so the junior tutor classified all the different compounds: propanol, ethanol, methanol, methane. Alkanes have very weak intermolecular forces, hence they have a high vapor pressure and are volatile. Alcohols, on the other hand, have a hydrogen bond, hence they have a lower vapor pressure and are less volatile than alkanes. Giving this, methane is the compound with the highest vapor pressure. compare the volatility of alcohols, we can look at their unbranched carbon chains. As these lengthen, dispersion forces can operate between the alkyl chains, so the boiling point increases, making the alcohol involatile. Hence, the ranking of the given alcohols in order of decreasing vapor pressure is methanol, then ethanol, then propanol. Okay, and then they just had the same answer as me. So this solution is correct. Okay, so question 4. For each solute, which will be the better solvent, water or carbon tetrachloride? Okay, so first let's draw our two solvents. This is water, and oxygen is more electronegative than the two hydrogens, and it has two lone pairs, so we can draw a non-zero dipole moment going towards the direction of the oxygen, showing that the oxygen is more slightly partially negative, and the sides with the two hydrogens is partially positive. So we can say that water is polar. On the other hand, if we have carbon bonded with 4 chlorines, each chlorine atom is more electronegative than the carbon, but the fact that they are all pointing in different directions just shows that all of their dipole moments will cancel each other out. So therefore we can say that carbon tetrachloride is nonpolar. Okay, so if we remember that like dissolves like, meaning that polar molecules will dissolve other polar molecules, and nonpolar molecules will dissolve other nonpolar molecules, then that can help us answer the question. So let's start off with C6H6. Oh, sorry. I think it should be C2H6. Well, either way, this is just a simple hydrocarbon, only containing carbon and hydrogen bonds, and even the electronegativities between carbon and hydrogen, they are pretty similar, so the difference isn't that noticeable. So therefore, this hydrocarbon can dissolve in the nonpolar solvent, carbon tetrachloride. For B, we just have a simple iodines bonded to each other, a diatomic molecule. So obviously they are identical because they are the same atom. So there is no dipole moment. So therefore this will also dissolve in carbon tetrachloride. C is sodium sulfide. So sodium is a metal. So already we know that these bonds are ionic. And every ionic molecule is able to dissolve in water. Because if I were to draw out the charges, it would look like that. So this is polar. So this is able to dissolve in water. And then lastly, we just have methanol. So our oxygen is more electronegative than the CH3. So I can draw a non-zero dipole moment towards the direction of oxygen. So this is a polar molecule, so it's able to dissolve in water. Okay, so the junior tutor said polar solutes dissolve in polar solvents and non-polar solutes dissolve in non-polar solvents. Water is polar, carbon tetrachloride is nonpolar. C6H6 is nonpolar, so carbon tetrachloride. I2 is nonpolar, so carbon tetrachloride. Sodium sulfide is polar, and methanol is polar, so they both dissolve in water. So the solution is correct. Okay, so on to question number 5. Phosphorus pentachloride decomposes according to the chemical equation. 0.215 mole sample of phosphorus pentachloride is injected into an empty 2.5 liter reaction vessel held at 250 degrees Celsius. Calculate the concentrations of PCl5 and PCl3 at equilibrium. AC is equal to 180 at 250 degrees Celsius. Okay, so first I'm going to write the reaction down. Phosphorus pentachloride gas makes phosphorus trichloride gas plus Cl2. Let's try to make it fit. Just move everything over. Okay, so the equation is already balanced. There's 1 phosphorus on each side and 5 chlorine atoms on each side as well. So now I'm going to make actually first I will find the concentration of our reactant. So I'm going to do it down here. So they give us the number of moles of phosphorus pentachloride, which is 0.215. And they also give us the volume of the reaction vessel, which is 2.50 liters. So to find the concentration of phosphorus pentachloride, it's going to be the number of moles divided by the liters. So this gives us a concentration of 0.086 moles per liter. Okay, so now I can construct an ice table with the balanced equation that we have. So the initial concentration of our reactant is 0.086, and the initial concentrations of both of our products is 0, since we start off with 0 product. The change in the concentration of our reactant is negative X, and the change in the concentration of our products is positive X. So lastly, at equilibrium, it will be 0.086 minus X, and the concentrations of our products will just be equal to X. Okay, so now let's write down our Kc expression. So Kc is equal to the concentration of phosphorus it's going to be the products divided by the reactants. So phosphorus trichloride times the concentration of Cl2 divided by the concentration of PCl5. Okay, so the Kc value is 180. And if we were to plug in our x's as the concentrations, we get x squared over 0.086 minus x. Okay, so now we can rewrite this as a quadratic and if we use the quadratic equation or a quadratic formula calculator on the internet, we can get x is equal to 0.086. So you'll find two values of x. One of them will be negative and one of them will be positive. And since we can't have negative concentrations, we go with the positive value. Okay, so the last step is just to plug in x into our concentrations at equilibrium. So the concentration of our reactant at equilibrium is equal to 0.086 minus 0.086. So it's just going to be 0. And the concentration of PCl3 at equilibrium is equal to 0.086. Is also equal to the concentration of our chlorine. Okay, so let's see what the junior tutor said. The reaction given is already in a balanced form. To solve the concentration of PCl5 and PCl3 at equilibrium with the given conditions, it is helpful to use the ICE table. For initial, given that there are 0.215 moles of the sample that is injected at 2.5 liters, concentration of phosphorus tetrachloride can be computed via solving its molarity. 0.215 divided by 2.5 liters gives 0.086 moles per liter, while the concentration of the products at the initial state will be 0. For the change in concentration, let the concentration of the sample be x by the time it achieved equilibrium. Thus, to find the change in concentration of the sample will be 0.086 minus x. For the products, there will be a concentration x after the reaction. At equilibrium, concentrations of the elements present in the reaction can be related to Kc. Substitute all the values we currently have, And they got x squared plus 180 x minus 15.48 is equal to 0. Solve for the value of x using the quadratic formula, where a equals 1, b equals 180, and c is equal to minus 15.48. They got an x value of 0.085, and they just did 0.0686 minus x, so they got 0.001. So when I got my x value, I just rounded up, but they rounded down. But the solution is still correct. Okay, so question 6. How do you convert the measurement of 2 days into seconds? Okay, so let's just write down all of the different conversion factors we need to do. So 1 day is equal to 24 hours. 1 hour is 60 minutes. And 1 minute is 60 seconds. So if we start off with 2 days, we can convert to hours by multiplying 24 hours in 1 day. We can convert hour to minutes to multiply 60 minutes in 1 hour. And then we can convert minutes to seconds by multiplying 60 seconds in 1 minute. So you know you did it correctly if all your units should cancel out nicely. So it's pretty much 2 times 24 times 60 times 60, which gives us 172,800 seconds. The junior tutor said, to execute the conversion from days to seconds, use the following conversion factors. Thus, to convert 2 days into seconds, you get 172,800 seconds in 2 days. Yep, so the solution is correct. Okay, so question 7. How can I calculate the pH of NaOH? So sodium hydroxide is a base. So we can't just use the pH is equal to negative log, because when NaOH dissociates into its ions, you get sodium plus a hydroxide. Okay, so I'll write an example of how we would go about finding the pH of this basic solution. Let's say we had 0.1 molar solution of NaOH. If we have the concentration of NaOH, since everything reacts at a 1:1:1 ratio, the concentration of NaOH is equal to the concentration of our OH minus ion, which is also equal to 0.10 moles per liter. So first we can find the pOH, and to do that it is negative log of the concentration of our OH minus ion. So plugging it in, negative log of 0.1 is just equal to 1. So the second part of the question, to solve for pH, this is equal to 14 minus the pOH value. So 14 minus 1, which gives us 13. So the junior tutor said, sodium hydroxide is a strong base that dissociates completely in an aqueous solution. It has the dissociation reaction, NaOH makes Na plus OH minus. Definition, pH of a solution is the measure of the concentration of hydronium ions. As the formula, negative log is the concentration of H3O plus. However, for bases, we must first compute for its pOH. Once the pOH was already solved, we can now compute for the pH of the solution. Yep, so they have an example with 0.2 moles per liter of NaOH. Since 1:1, we do pOH is equal to negative log of 0.2, so they got 0.7, and a pH of 13.30. Yep, so the solution is correct. Okay, so question 8. This asks, what is the molar volume of a gas? So we can solve this using PV equals nRT. At standard pressures, I can just rearrange it now. Okay, so standard pressure is 1 atm. For number of moles, I'm going to substitute 1 mole. R is just the ideal gas constant, and it's equal to 0.08206, and its units are in liters times atm divided by mole times K, and temperature is 273 Kelvin because this is the 0 on Kelvin scale. So if we solve for this, we can get the molar volume, which is 22.4 liters. And the junior tutor said, assume that we have 1 mole of gas present at STP, T is equal to 273, P is equal to 1, and they use the ideal gas law and also got 22.4 liters. Yep, so this solution is correct. And I think we have time for one more quick question. Question 9, what is a pure substance? So a pure substance has constant composition and properties that are constant throughout the sample. Okay, so let's see what the junior tutor said. Matter can be divided into two groups depending on the chemical content that they have in terms of purity and homogeneity. Matters labeled as pure substances are the ones that are composed of a pure type of atom or molecule. Because of this property, they are also homogeneous. This type of substance can be classified as an element and a compound. The difference between the two is their capability to break down into smaller components. Elements can't be reduced to smaller components even by any physical or chemical methods, whereas compounds are substances composed of two or more elements combined through chemical means. Since they are built up with a number of elements, these components can be broken down into elemental pieces. Pure substances have different properties, one of which is its homogeneity that makes it have uniform composition on its bulk form. Another is its fixed boiling and freezing point due to the uniform content of the matter. Common examples of pure substances are metals comprising one element such as gold, copper, silver, etc. For compounds, the classic example is water and salts. Yep, so the solution is correct. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, go ahead and give it a thumbs up and a comment. And don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.